in an easy way to understand it, it's looking at the uptime over the total period. So if you think about a piece of equipment, and let's just take a generic example that it fails once per year and it's down for 6 months of the year. So we'd have the uptime of 6 months, downtime of 6 months. You take that over the period of the year. So 6 months over a year, you'd have a 50% availability, which is pretty terrible. Sometimes that happens, right? But that's how the availability would be arrived at. And a lot of times when we're looking at 5 9's, we're looking at that to support contracts, or 3 9's to support contracts. So that's kind of the driver of the availability. And so if you think about 5 9's over the period of a year, right, that's 5.26 minutes of downtime. So really have to zone in, and you can't really have any failures or you're going to incur some problems there. You look at 3 9's, if there's 8,760 hours in a year, that would be 8.76 hours per year of downtime. So a lot of times that's looking at one failure over a long period of time that would say equal an hour or equal a multitude of hours. But that's what we're looking at when we say 3 9's, when we say 5 9's, and those are the targets that we're looking to hit there. When we think about availability, right, we think first about the boundary conditions. What are we trying to model? So we start all the way at the utility, looking at their substations, and then move all the way to the rack, and we pick up the mechanical systems along the way. So the chiller and the craws, and make sure that when we get to that rack level, we hit that 5 9's. And so, like I mentioned with the example equipment item, say it fails once per year and is down for 6 months, we characterize all the equipment throughout the entire data center with those characteristics. So then we build the model from start to finish with those hundreds of pieces of equipment, and we need to understand the interrelationship of those two. So we're thinking about n+1, 2 by 100%, what is the redundancy throughout? And then we model more complex aspects like some of the storage characteristics. So if you have a BESS system or a generator tank, you need to know how long that's going to discharge. And then we layer on top of that some distributions to that equipment. So we need to simulate the real world randomness that gets taken into account. So when you think about the BESS energy storage system, say you have a piece of equipment that fails and it's down for 20 minutes, right? With the BESS, say you have a 30-minute BESS, and if you just take an average model, right, you have a failure for 20 minutes, the BESS always picks it up because it's 30 minutes long. But we want to simulate that real world randomness, that different failure modes could come into play, so that you'd take that 20 minutes and it could be a 40-minute downtime. And so we want to make sure we capture all of that risk. Same thing with the generator fuel storage, that maybe you would have an outage that's more than 24 hours. So we make sure that, okay, is there a fuel supply contract in place? And if not, how would we handle something like that? The data is always one of the tough challenges, is getting the right data to model reality, right? So we talk to a lot of vendors over many projects and understand, okay, how is your equipment performing? How has that changed? For generators, maybe that's a change from the emergency backup type role to a continuous generation, and understanding how the characteristics change there. And so we bring those in. We also consult databases like IEEE 493, IEEE 3006 from the Institute of Electrical and Electronics Engineers. And then some of our own primary research, the Electric Power Research Institute, offshore reliability databases. And we bring all that data together and then use engineering judgment to make sure that it fits reality. And then, of course, we talk to the utility as well. Make sure those incomers are what changes a lot of times with the topology. So we model their substation. We look, how often does it fail? Are you having any voltage issues? And make sure that we fully understand the design. And then in terms of the challenging part beyond the data is the actual model. So what assumptions do we go into the model? Just to give an example, when we look at modeling chillers, right? You have, first off, are you going to model the worst case conditions, or are you going to model more of an average case condition to make sure you handle the risk? A lot of times we move towards an average case type model so that we properly account for the changing ambient conditions. But not only that, if you have a fan failure, right, you're going to lose some capacity of your chiller, right? And in the model, most models, they just go ahead, you're going to send someone out, they fix it, and then it comes back online. When you're at the worst case, you might need to strategically leave that chiller alone and wait to bring it back to service before excuse me, before you move on to the next item. So we want to make sure that those repairs are scheduled strategically, as that can make or break your 5 9's model, right? You have 5.26 minutes a year to deal with. And so if you're N+2 on your chiller design, you could expose yourself to 3 failures if you don't model that reality correctly. And so we want to make sure that all those assumptions line up and that they properly reflect reality. And that's a large collaboration that we really enjoy exploring and really diving deep into those details, make sure everything reflects correctly. So the beauty of using the Monte Carlo simulation that we do is you can quantify those directly. So we can come up with a base case design and then say we want to pluck the LV generator out or introduce some different automation. We can model directly what that availability is at the start and then what the availability is at the end. And so then when we go through the model, we can say, okay, what's driving the unavailability in each case, come up with those different results set, and then iterate on that design so that we fully understand what's going on versus relying on like a design standard where, okay, it's currently maintainable, you have N+1 on these, 2N on these, and then you're going to hit 5 9's versus if we're simulating, we end up with the exact result that this is where we're going to end up. And then when we simulate off of it, we can see that delta and we can actually quantify that risk and assign it a value so that you end up with a cost benefit analysis at the end of the day. Not just did you meet your target, but I'm getting the value for the money that I'm investing in here. And that can lead to upstream effects too, that say I'm putting in on-site power with a particular data center, really you should model from the start to the finish. We've seen a lot of on-site power where you're targeting 3 9's, right? And that'll make it 5 9's at the rack, which is great. But if you model it all at once, maybe you can shed a generator up top and then save that money and still be 5 9's at the bottom. And so that comprehensive simulation can really yield a lot of benefits and really help us refine the exact pieces of the design there. Yeah, so we've explored all kinds of different designs, which is really what makes my job fun. At the end of the day, is this is not like a cookie cutter design anymore. We're moving into a fast paced, evolving design. We're moving from 5 9's to 3 9's, sometimes 4 9's. We heard 6 9's thrown out the other day. That's really on the top end. But I kind of look at case studies starting with the high voltage. Based on where you are in the world, that substation topology can look different. And so understanding how those impact the design. We've seen breaker and a half be kind of the go-to. It has a lot of good reliability there, 2 utility connections coming in. But then adding the on-site power, maybe a single utility. We've seen all those are viable options, just depending on how your design works there. And then we move into the high voltage transformers. If you have multiple sites, a lot of times we've seen that a critical spare can be worthwhile in that case. If you're just a single site, that's where that cost benefit analysis of, okay, if you're a smaller site, do you really procure that critical transformer? And we've kind of seen it can be 50-50 that way, especially because a high voltage transformer can be a high impact, low probability event is what we call it. So very likely it's not going to occur within the entire life of the data center. But you still need to account for that risk because if it does occur, your lead time on that transformer could be 3 years, which is just astronomical. I was talking to one of my colleagues the other day. Even a high voltage like SF6 breaker is now 3-year lead time. So that really can impact things. Going to the medium voltage, how far can we push that loop out? So we've seen a lot of designs, single digit positions. Can we move that into the double digit positions? We've seen there's some viability there, but we move into beyond just the typical operation. Now we're exploring from a concurrent maintainability standpoint, does that still work? Then the same on the LV generator side. Can we push that out to 10 positions or so and make that work? And again, the challenges of concurrent maintainability, and that's where we see it going. And then from the 3 9's perspective, plucking out the generator can work, but then introducing automation on that medium voltage loop to then make the transition easier, bringing in a redundant feed we found effective. So a lot of case studies we've been exploring. How do we refine the design, make it more competitive in the industry? Because that's ultimately what we're going for. If you can remove one of your generators or even decrease that redundancy, that can have huge financial implications as it translates across. So I've kind of seen two shifts a little bit. So the first is moving away from a standard design. So you knew you had a standard design that hit the 5 9s or the 3 9s, but being more flexible with that design. And so using that simulation based approach. And then beyond that, moving into design exploration. So if you run into a problem, the best type of problem to run into is the problem that you already have the answer to. So when you move into that exploration and go deeper, say your typical design has two utility connections. We already know the answer for a one utility connection and how good it needs to be. That can allow agility that moves a lot quicker in the marketplace. All the studies I'm on, everybody says we want it yesterday. So if you can have some of those answers prepared beforehand, that can just be a huge game changer. And so having multiple designs so you can pivot quickly for sites. So when you come in, okay, what's a reasonable on-site power design that I can usually start from a template standpoint? What are some of the levers I can pull in my model to make it work out? I'm space constrained. Okay, what can I do? And having those answers ahead of time could just make a huge difference. And I think that's where the industry's going. And then the other piece on top of that is, going into next level considerations. So a lot of our analyses, they look at typical operation. That's what people are benchmarking to. And with the lead times of this different equipment, we're going to have to go into a next level of design that there's risk there that's not being accounted for when we think about critical spares, what's being maintained. And I think that's where the industry's going to head here. Going forward, I mentioned a little bit, I think it's going to go into operational availability beyond the typical operation. And then we've seen some of it, we like to stay in the design side. That's where it makes the most sense, right? You're going to get the best bang for your buck, figure it out early. But we have seen in the construction space as well that, the site can change very quickly. There can be hidden factors and we need to account for those. So just one example that comes to mind is we've simulated a lot of designs that, okay, we're going to build it all out. This is what it's going to look like, and it's going to hit the 5 9s availability. And some of the hidden pieces of that is, okay, we can't get the second utility line till building 3 comes online. So building 1 has a single utility, and we can help simulate, okay, did we hit the availability there, and what potential design changes can we make along the way? Not ideal, but that's how we could step in and help there. And then say you have now on-site power and your generator gets delayed to the pad, your redundancy might change there. And so we can help simulate those as well. So that day 1, day 2, day 3, day 4, all those different steps along the way is where the industry's headed to validate that, okay, we hit our number of 9s there. And then lastly, I think just having a bigger, fuller understanding of the data center design. So we understand, okay, where are my pain points? Where are my single points of failure? What levers can I pull? And then what is the cost benefit of making these design changes? And having that quantification of the risk can just be really effective in developing the designs of the future that are going to be the most competitive in the marketplace.